Hello, everyone, and welcome to Revolutionizing Soil Moisture, a new holistic approach for higher accuracy. Today's presentation will be 20 minutes, followed by 10 minutes of Q&A with Leo Rivera, research scientist here at Meter Group. If you have a question for Leo, type it into the questions pane at any time during the webinar. We'll be keeping track of these to ask during the Q&A. Please don't be shy and submit those questions. We will send a link to the on-demand webinar and the slides for you to review as soon as they're available. So without further ado, I'll hand the microphone to Leo Rivera.
All right, thank you. Good morning, everybody, or good afternoon to those of you that it's afternoon. Thank you for joining today's presentation. As Brad said, my name is Leo Rivera. I'm a research scientist here at Meter Group. And today I want to discuss one of my favorite topics, which is, of course, measuring soil moisture. And today's presentation is not just going to focus on measuring soil moisture with not just the sensor technology, but it's also going to focus on taking a more holistic approach to everything and addressing several issues that can potentially result in bad soil moisture data. So I want to start with this slide. So for the past 20 years, we've spent developing and designing and engineering soil moisture sensors. We've had a lot of time to learn a lot of things. Let's, for example, start with our EC20 soil moisture sensor, one of the earliest soil moisture sensors we developed and released. And it's this ruler-looking soil moisture sensor here on the left. It was one of the first soil moisture sensors that we came out with. And it was good for what it was at the time, but there were several issues with this sensor design. One, as you can imagine, a sensor like this is quite hard to install in the soil, especially in hard soils. We usually had to use a pre-insertion tool just to get this sensor in the ground, and it wasn't quite as durable as we needed it to be. It also operated at a different frequency. It operated at 20 megahertz, which left it susceptible to a little more texture sensitivity and sensitivity to salinity as well. We later developed a soil moisture sensor called the EC5, which actually has been one of our most popular and most successful soil moisture sensors, and is well used and has been deployed all around the world. And one of the goals, of course, with this soil moisture sensor was, one, we wanted to get rid of the texture and salinity effects that we were seeing, and so we moved to a 70 megahertz frequency for operating at. You also can see that we changed the design to make it a little more easy to insert into soils. And so that's where these two sharpened tines come in. And that was definitely a big improvement, and that definitely made it easier to work with this sensor. But even this sensor still had its issues. It's not quite as durable as we would like it to be. But it was really great for what it was. And we then started adding, working on sensors that had multiple parameter measurements. For example, the 5TE that measures soil moisture, temperature, and EC, because as we've learned, it's important to measure other parameters along with soil moisture. Temperature is very critical and is very important to go along with soil moisture. And EC is also very useful in trying to do things like measure pore water EC or just monitor solute movement in soils. But again, with this PCB design and with some other things about this sensor, we learned that it quite wasn't durable enough. And so we started working on some stainless steel needles, and we have some other versions, the GS3 that first came out, and the GS1. And those were definitely some major improvements in durability, but even those sensors still had some areas that they could be improved on. So let's go to this next slide. So here we have actually two examples of some of the things that we've seen in the field, and that's the things that helped us learn what we needed to do to make our soil moisture sensors more durable. This picture on the left is actually a 5TE soil moisture sensor that's been eaten by ants. This was an issue with the macro melt that was used on that sensor to protect the electronics. It turns out that in some places, ants really like to eat that material. And so obviously that was not a durable enough material for these soil moisture sensors. So we actually moved to an epoxy fill for these sensors to help make those more durable and survive better in these types of environments that they were failing in. And so that was definitely an improvement, but they still had room to go from there. And on this picture on the right, you see an example of our GS3 sensor where one of the tines was broken. So the GS3 sensor was designed to be a little more rugged, but it wasn't quite built to be rugged enough. And we did see, on occasion, we've seen these types of issues where the tines are getting broken. And so we knew we needed to make improvements in that area as well. And so that's really everything that we've learned over the last 20 years is what's gone into the design of our new TEROS 12 soil moisture sensor. And so we had a lot of goals. We wanted to make the sensor more durable. We wanted to make it easier to install. And we'll talk about that in just a little bit. We also wanted to improve the sensor-to-sensor variability. So traditionally in the past, what we've done with soil moisture sensors is we've calibrated them using liquid dielectric standards in our production facility. And the liquid dielectric standards are a little hard to work with and not quite as tight of reproducibility as we'd like to see. So we had a goal of actually moving to a new calibration process that actually uses is an electronic calibration process using different levels of capacitance. And so we moved towards that new calibration process in production with the TEROS 12 sensor, and that's really helped improve our sensor-to-sensor variability. And at the same time, it's also streamlined the calibration process, which is allowing us to bring the cost down on these sensors. And so all in all, it's an improvement for the customer in terms of performance as well as price. Of course, we wanted to make the sensor more robust, and I'll talk a little more about that here in a second. We also wanted to optimize the form factor to make it easier to install. And one of our main goals was to be able to install this sensor down a borehole. And I'll talk a little bit about that here in a few slides about some of the strides that we've made there, but you'll see why this form factor comes into play. One other area that we wanted to really make some market improvements in is the robustness of the sensor firmware, actually. So in this day and age, as we see more and more digital sensors, we see more risk of things like firmware corruption. And obviously, when sensors in the ground, and if that fails due to firmware corruption, that's not something we want to see. It's not ideal. So one of the things we've done with the TEROS 12 is we've actually moved to a new microcontroller that has really improved the robustness of the sensor firmware, really helping us get rid of that potential risk of firmware corruption. So here's some examples of some of those physical changes that we've made to the TEROS 12 to help make it more robust and help make it fit some of these goals that we were trying to reach. One of the things we did is we actually reinforced the PCB on the inside of the sensor. And what that does for us is it actually provides a more secure mounting point for the needles, helping to make them more durable and less susceptible to breaking. And so that's one area that we've made a pretty big stride in terms of robustness. It also helps protect the electronic components in case there is any stresses put on the sensor. Say the sensor is installed in a high traffic area or maybe under a roadbed. This would help prevent any components from being damaged. One other piece was actually sharpening the needles. So you'll notice if you're familiar with our older sensors like the GS3 or GS1, the needles on the TEROS 12 have a significantly sharper tip. And the main goal there is actually it helps make the sensor easier to install, especially into hard soils like hard clays. That sharpened tip just really cuts better into the soil and it makes it easier to install the sensor. We've also moved to embedding the thermistor in the needle. So traditionally, our temperature measurement has been on the PCB itself and usually in the sensor body. So that larger mass takes more time to come into equilibrium with the soil temperature. Now, at deeper depths, this isn't very critical because temperature changes at deeper depths in soil are usually slower. And so usually that wasn't an issue. But if you were making near surface measurements, this was could become an issue. Also, when measuring, if you're trying to measure, say, in pots and you're installing the sensor into the side of a potted plant, you don't want to have the temperature sensor on the sensor body because that's not in the soil. So moving it into the inside of the thermistor actually helps us make sure we're actually getting soil temperature and not temperature of the sensor body. And then one last piece is we moved to this hard plastic body. And that one is critical in making this sensor compatible with our borehole installation tool, as well as helping to make it more durable. One other piece of major improvement with this sensor is increasing the measurement volume. And as everybody knows, soil moisture is very spatially variable. And sensors that have a small measurement volume tend to have issues in really capturing the soil moisture of an area, because it could be very localized. And so so one of our main goals was to really try and improve that measurement volume, help us better encompass the variability of soil moisture. And so we were able to do that with the TEROS 12. The sensor actually has a 1,010 cubic centimeter measurement volume, which is a large improvement from some of our other sensors. And it really more so comes in line with what our 10HS sensor had or has, but in a smaller form factor and a sensor that's easier to install. So this is a pretty major improvement for these sensors. So let's just look at some of the data from these sensors. So here we're looking at actually our soil calibration data. So what we're looking at here is calibration data in 4 different soil types at 3 different salinities. Of natural salinity from the soil, 3 decisemen and 7 decisemen in bulk, pore water EC. And what you see is that the calibration data is fairly tight, considering how much we've changed the texture and especially the EC changes. And so this has to do with our 70 megahertz frequency that we operate at, that it really helps minimize some of the effect of soil texture and soil texture and salinity. And so really what this means for you is using the mineral soil calibration that we offer is going to work well in most cases. Now, if you really want to improve your accuracy, you can still do a custom calibration, and that will definitely give you the best accuracy possible. But in many cases, this calibration will work well. Let's take a look at some of our field data from one of our test sites. So here we actually have a profile of sensors that were installed at 20, 40, 60, 80, and 100 centimeters. And these were installed down a single borehole. And what we're looking at here is several rainfall events. And we see very good, clean, consistent data. We don't see any strange blips in the data. Everything looks as we would expect it to look, considering what we were seeing in the environmental conditions. And if we zoom in on a rainfall event from December 19th, what we would hope to see is that as a rainfall event occurs, and this was a fairly heavy rainfall event, I can't remember exactly what it was, but what we see is the sensor in port 1, and you can see it is that darker blue line right here, is the first to respond to the wetting event, which is what you'd expect to see. And then you see port 2 begin to respond to the wetting event from the rainfall, and then it moves down to port 3, which is our 3rd deepest sensor. And then eventually, over time, the wetting front continues to migrate its way down, and actually begins to make its way down to the 4th sensor, and that at about 80 centimeters. And as you can see, this deepest sensor still hasn't responded, so the wetting front hasn't made its way down that way. And then later, as we get another rainfall event on 12/29, we begin to see, again, that same pattern of responses. And then we actually get the wetting front moving deep enough down to the deepest sensor to where we actually get a response from that sensor. So what about sensor installation? And I think this is another key component to getting good soil moisture data, is really focusing not on just the sensor technology, but trying to improve the installation process. So traditionally, when installing soil moisture sensors, we typically would dig a large pit. And usually what that's going to surmount to is a significant amount of site disturbance. Usually we're having to remove quite a bit of soil. It's very time consuming. I mean, this can take several hours just to do one installation. So this is a traditional method. And usually with this pit method, we're going to install sensors into the sidewall of that pit. Now, the advantage of this method is we can install lots of sensors in one spot. So For example, if we were doing a sensor comparison study, this is great. But in most cases, this is not what we're trying to do. We're trying to look at soil moisture across a large field. So that means we need to install soil moisture sensors at several locations. And as you can imagine, if you're using this traditional pit method, that's going to be very time consuming, and it's going to result in a lot of disturbance to the site. I mean, just if you look at this picture here, this is to try and better paint the picture of the amount of site disturbance. When you look at the surface, you can see we've significantly disturbed the soil surface. We've destroyed the macropores, any of the structure, and it becomes very hard to repack the soil to the same density that it was at before with this pit method. And so it makes it a little bit hard to be confident in the soil moisture data early on. So one of our goals, of course, was we really wanted to focus on improving the installation method. And that's really where this tool came out. So one of the tools that's coming out with the TEROS 12 is the borehole installation tool. And what this tool allows us to do is actually take our TEROS line of sensors, so right now the TEROS 12, and we can set different installation depths using this base plate here, and really adjust where we want to install our soil moisture sensors. So the way this process looks is we're able to install sensors in a 4-inch borehole. So you'd start by augering your 4-inch borehole down to your deepest depth that you plan to install with a little bit of extra just to make some room for the tool. We would then use the installation tool to actually install the sensors in a profile. And what's nice is this gives us a customizable profile that we can set based on what our knowledge is of the area. So if we want to measure in different soil horizons, or we have crops with different rooting zones and we want to adjust our measurement depths, this allows us to set a customizable profile in a single borehole. And this really speeds up the installation process, but at the same time, it also gives us a more precise insertion of the sensors. So I know typically when I'm trying to install sensors by hand, my hands are very shaky, or it's hard to make sure that you get a nice straight insertion of the sensor. So the borehole installation tool actually gives us a very precise insertion of the sensor into the sidewall of the borehole, minimizing any sensor movement and any potential for gaps forming around the sensor, which is very critical. And overall, what's most important is it really minimizes our site impact. So here you can see where we've installed 2 different profiles of sensors, and the areas that we did the installation you can barely see the areas that were disturbed. And so that's really kind of the important part that we're trying to paint here, is that we're able to minimize site disturbance. So here's just a video that kind of shows that whole process of setting our installation depths, augering the hole, and just shows how the installation tool works. So you can see how you lower the tool into the profile, into the borehole, and then the tool inserts the sensor into the sidewall very precisely, and then releases it, and then you just pull the tool back out. So it really helps simplify the installation process and really speeds it up. In most cases, most installations can be done within 30 minutes to an hour in a single profile. So I think one other piece of data collection, one other piece of soil moisture data quality that I want to talk about is actually kind of addressing the data collection process. So let's go into an example here. Here we have an example with using the TEROS 12 with the EM60G data logger. So the EM60G would collect the soil moisture data over time, and then that data is transmitted via the cell network to the cloud, and it's stored for later access, and then can be used to make decisions on whether we need to irrigate or various other things. That data that can then be accessed using a tool like Zentra Cloud, where we can actually visualize where our sites are and interact with the data loggers. We can make changes to the data logger configurations, and we can view quick snapshots of the data from the last 24 hours, or we can go in and look at more detailed data from the sensors, looking at the past week's data or the last year's data, allowing us to quickly view data, make decisions, and just be able to view what's going on in our fields. One other piece that's really nice about this is, in this day and age where typically a lot of our research projects are larger research projects with several collaborators. And so with this tool, it actually allows us to easily share our research sites, our data, with other collaborators. And you can share the sites with other people and adjust their settings to whether you want to have them have administrative settings where they can actually make changes, or if they just want to have user settings where they're just viewing the data and they can download the data. And so that allows us to really be able to share data with our colleagues easily. And I think one other piece of data quality that I think where this really helps us is knowing when something goes wrong. So our soil moisture data is only good if it's actually there and if it's actually measuring. And in many cases, we sometimes won't go to a site for maybe a month, especially depending on how accessible the site is. It may be a couple months before we go back out. So what happens if something goes wrong? Well, we need to know that. And so with tools like this, we can actually view our data and see what's going on with the data and know if there are issues with a sensor and if we need to go out and make a site visit, or if a logger is having an issue with batteries or something along those lines. So this really helps us ensure that the data is actually being collected and that we don't miss potentially several weeks to several months worth of data. And so I think that's another key piece of making sure we have quality soil moisture data, just making sure that the data is actually there. So that actually wraps up the presentation. And we'd like to use the next 10 minutes to take some questions from the audience. Thanks to everyone who sent in questions already. There's still time to submit questions now if you'd like. We'll get to many as we can before we finish. So let's get to our first question. So one of our first questions actually is do you plan to introduce wireless soil moisture sensors? And that's a really good question. Right now, the answer to that is not yet, at least not for field applications. We do see some wireless soil moisture sensors getting ready to come out for other applications like greenhouse applications where the sensors aren't getting buried. One of the main issues with field applications with trying to use this wireless soil moisture sensor is that if we're installing the sensor at any type of depth, it's very hard to transmit the signal up through the soil. And usually that means we're going to also have to make sure the sensor is staying powered for a period of time. And so it becomes a little tricky. And so there's not a lot that we're moving towards in that area yet, at least not for field applications. So our next question is, can the TEROS 12 be installed in core slabs? And actually the answer to that is yes, it can. And we actually do have a calibration for core. So our soilless media calibration actually works for this type of media. And we have so it would work well in this application. The main thing you want to make sure is that the size of the slab encompasses the measurement volume of the sensor. So as long as the slab is a 10 centimeter slab, it should be okay. And another question from the same person is, can the software communicate with Argus systems so the data can be viewed? And that's a really good question. And actually, I think there is a potential for that. I mean, we have APIs that allow access to the server data to be able to pull that data in. And so I think that's a possibility. We probably need to look a little more into what that would take. But yeah, that's take a little more thinking. But if you do have a question, if you do want to address that a little further, please, email one of our support people and we can look into that a little more. Our next question is, how do we recover the sensors installed with the tool? And that is a really good question. And that actually becomes a little tricky. Usually most of the sites that we're dealing with are designed for longer term deployments. So we're not usually concerned with recovering the sensor. But I have worked with people in the past where typically what they've done is they've augered a little off to the edge of where they originally installed the sensors. And then that allows them to pull the soil away without damaging the sensor. And and then they can pull the sensors out that way. But it is tricky and probably a little labor intensive, but it is possible. All right, so let's move on to the next question. So I guess this question is, are you working on an improved version of the GS3? Let's see, sorry, I need to expand this. There we go. The GS3 is great for spot measurements because its influence volume is only 4 needles. That's a really good question. So the Terras 12 actually is designed to be the replacement for the GS3. And what we found is that it can be used for taking spot measurements. Now, I should state that, our sensors don't have replaceable needles so if they do, if you do bend a needle or if you, do damage a sensor, it's hard to fix that. Whereas there are some other sensors that do have replaceable needles. So, this is something you have to be aware of when you're using sensors for spot measurements. But yeah. So let's move on to our next question. Sorry, there's got a lot of questions that we got to get through. And if we don't get to all of your questions, we apologize, but you feel free to send them in later. So I guess this next question is, what's the approximate cost of the installation tool and sensor? So in the US, we actually have 2 options for the installation tool. It can actually be used as a rental, and it's usually about $500 a month per rental. But we do also have where with larger orders, we have different options for the installation tool. To purchase the installation tool, it's about $3,000 because it's a pretty expensive tool to make, as you can imagine. And the new sensors are around $225. But please feel free to send in, send in an email for a quote if you need better information on that. So we'll move on. I think we have time for a couple more questions. One of our next questions is, how far apart do you need to install the Terras 12 sensors from one another when installing your profile? And the main thing you want to ensure there is that the sensors aren't within their measurement volume. And so typically, as long as the sensors are within or are at least 6 centimeters apart, that means they'll be outside of interfering with each other's measurement volume, then you should be okay. Our next question is, what is the comparison volume of influence between the GS1, the GS3, and the Terras 12? So that's another really good question. So the GS1 actually has about a 500 cubic centimeter measurement volume. The GS3 has about 180 cubic centimeter measurement volume, and the Terras 12 has about 1,010 cubic centimeter measurement volume. So if you're just comparing, the Terras 12 is about double that of the GS1, and more than 5 times that of the GS3. So I think we have time for 2 more questions. This next question is, what is the comparison of the Terras 10 and the Terras 12? And I have a feeling I may have mentioned the Terras 10 by accident, but the Terras 10 is actually going to be an analog version of the Terras 12 sensor, so it's only going to measure soil moisture. That's actually something that we'll be releasing in the near future. So that actually will be a replacement for the GS1 with some improvements there. So that's the main difference there. And then we eventually will also have another version that will be a similar form factor to the Terras 10 with the 2 needles, but will be digital and will measure soil moisture and temperature. So I think we'll get to 1 or 2 more questions. When using the installation tool, what's important to consider in rocky soils? And that's a really important thing to be careful with. So one thing about the installation tool is it provides quite a bit of mechanical advantage. So when you're working in really rocky soils, you actually have to be aware of where you're installing the sensor and ensuring that you're not pushing it into a large rock. Because of the mechanical advantage of the tool, you run the risk of damaging the sensor. And so that's something you definitely have to be careful with. And And I think that should about cover it. So I'm sorry if I didn't get to all of your questions. There's quite a bit to get to. If you do have any other questions and you feel like you want to get them answered, please just send us an email and we'll get back to you. But thanks for joining us today. We hope you enjoyed the discussion as much as we did, and thanks for the great questions. If you would like more information on the TEROS 12 or would like to talk with me further, please consider answering the short survey that will appear after this webinar. Look for the recording of today's presentation in your email and stay tuned for future meter environment webinars, which includes a webinar coming in June, which will focus going more in depth onto sensor installation and keys there to getting good soil moisture data and focusing on several installation methods. And that'll be coming June 20th. And thanks again.